Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good morning all. It's my pleasure to introduce Diwakar Gupta, who's a student of Amin Vedat at UCSD. He'll be graduating real soon now and will be looking for a job. He's done work in distributed systems, network emulation, scaling and management of virtual machines and virtualized system infrastructure. He's got publications in NSDI and OSDI, including the most recent NSDI and the upcoming OSDI, and he's going to be telling us about some of that work this morning.
Thanks a lot, John. Good morning, everyone. Thank you all for coming. It's a pleasure to be here. So I want to start by describing what I think are two compelling problems. And in this talk, I'll show you how to address them using virtual machines. So the first one is the problem of protocol evaluation. So we were just talking about TCP. And one of the problems with TCP is that on extremely high bandwidth networks, it doesn't perform very well. Now, in the literature, several variants and enhancements to TCP have been proposed to address this problem. So let's say you wanted to test two different variants of TCP on a, let's say, 100 gigabit per second wide area link to see which one does better. How would you go about doing this? Now, traditionally, you could approach this problem in three different ways. Or you could try to get access to a real-world 100 gigabit per second link, if such a link exists. But even if such a link exists, it probably is not going to be easily accessible to everyone out there. You could try to do a complete software simulation, such as in NS2, but then you lose realism because you're not using real operating systems, real unmodified applications. And finally, you could use an emulation environment, such as ModelNet. So a network emulator allows you to experiment with arbitrary network topologies with unmodified applications and standard operating system networking stacks. But even in a network emulation environment, you are fundamentally limited by the bandwidth of the underlying network. So in this talk, I'm going to show you how to do such an experiment while preserving realism right in the comfort of your lab. So here's another problem. How do you test large systems? Here's a quote by Werner Vogels, who's the CTO of Amazon.com. And what he's pointing out is that in order to test a large system like Amazon, ideally you want to create a replica of the entire system and test on that replica. But what if you don't have the capacity to duplicate all that infrastructure? So typically we resort to doing small scale tests on a few number of machines and extrapolate from there. But the same problem exists in other domains as well. You don't have to be as large as Amazon. Let's say you're a company that makes a high performance file system and you are shipping this file system to clients who will deploy it in various kinds of deployment scenarios. So they might have different hardware, software configurations, and so on. So ideally, you want to make sure that the system is tested on all these possible deployment scenarios. Unfortunately, you have a limited testing infrastructure at your disposal. And furthermore, this testing infrastructure might be shared internally among several different teams who are doing the development. So each individual team gets even fewer machines to work with. And in particular, it might be impossible to test the system at a scale at which it will be deployed at using the limited number of machines you have. So in this talk, I'm going to show you how you can use a smaller infrastructure to test accurately, so test and replicate a much larger system, an order of magnitude larger system, in fact. So these are sort of the two problems that I'll be talking about in this talk. But where do virtual machines fit into the picture? Now, before I start talking about that, I just want to clarify the terminology that I'm going to use in this talk, because virtual machines mean different things to different people. So on a regular physical machine, we have various resources, such as the CPU, the disk, the memory, and so on. And we have the operating system, which is multiplexing these resources among different applications. In a virtual machine environment, instead of the operating system, we have a thin layer called the virtual machine monitor, or the hypervisor, which is responsible for managing these system resources among several different virtual machines. A virtual machine is basically a software abstraction of a physical machine, and each virtual machine can have its own operating system and application stack. We call the operating system that runs within the VM the guest operating system, and I'm also going to use the term domain to denote the virtual machine in this talk. The virtual machine monitor exposes a hardware-like interface to the virtual machine. So the guest operating system thinks that it's actually running on real hardware. So that's the sort of the model that we're working on. Now the concept of virtualization itself is quite old, almost 50 years ago now. But in the last couple of years, interest in virtualization has picked up significantly. In fact, a recent IDC report estimates that virtualization was already a $5.5 billion industry in 2006 and is projected to grow strongly in the near future. So it looks like this market is growing rapidly. But what are some of the things that are driving the adoption of virtualization? What are people using virtualization for? So here's a recent survey done by CIO.com where they asked people what are they using virtualization for in production IT environments. And by far the most popular use is for server consolidation. So by putting services on a fewer number of physical machines, you can cut down costs and increase utilizations. So that's one of the biggest driving factors. But the following couple of reasons, I clubbed them together and called them novel applications. And these are, I think, the more compelling reasons that will drive virtualization moving forward. And we'll talk briefly about both of these in the next couple of slides. So of course, in the past couple of years, server consolidation has become increasingly important. Over the past decade or so, the infrastructure costs of a data center have remained largely stable, but the administrative costs and the power and cooling costs have been increasing at an alarming rate. And so by consolidating your infrastructure, organizations can cut down on both these expenses. And in fact, VMware customers report that typical data center utilization for servers is in the 5 to 15% range. And using virtualization, they can bring it up to 60 to 80%, which translates to tremendous dollar value savings for organizations. But as I said earlier, I think virtualization is becoming increasingly more compelling for the new and unique applications that it enables. For example, because the virtual machine monitor exports different hardware interfaces, you can actually support legacy software, legacy hardware, even if the real hardware doesn't exist anymore. Go ahead.
Does server consolidation address the maintenance costs that we're talking about?
A little bit, and we
still have to manage each of those virtual machines just as much as you do the real machine.
Absolutely. So there's some maintenance cost that is constant overhead per physical machine, and there's some maintenance cost that is constant overhead per virtual machine. But the real story is that with these virtual machines, you get management tools to manage this virtualized infrastructure, and things like keeping the virtual machines updated, patching them becomes easier if you are operating in this virtual machine framework than if you were working with physical machines themselves. So while there is still some cost associated with managing virtual machine, the overall cost decreases because the dominant cost is the per physical machine that you have to manage in the infrastructure. But we can talk about that more later on. There are several other interesting applications in security. For example, you can do intrusion detection or full system logging and replay. Virtualization is extremely useful for development and testing. So if you're testing a patch for Internet Explorer, instead of testing on several different versions of Windows and IE and different combinations, you can quickly boot pre-created virtual machine images with all these different software combinations and use a single machine for testing. And finally, virtual machines can be created on demand and migrated from one physical machine to another. So this flexibility in how you provision resources allows you to build more agile infrastructure. So companies like Amazon and Mosso are using virtualization to build out their cloud computing infrastructures. The work that I've been doing the past couple of years has been mostly around virtualizations and spans both of these domains. The overarching theme in my research has been to allow you to do more with virtual machines by making it more scalable. So for example, by allowing more aggressive server consolidation or by addressing some of the applications that I mentioned earlier. So in this talk, I'll talk about mostly the novel applications that virtualization enables, two examples of which I gave earlier. I've also done a bunch of work in server consolidation. So for example, by improving the way virtual machines monitors manage memory, you can actually increase the number of virtual machines that can be supported on a single physical machine, allowing for more aggressive server consolidation. I worked in performance isolation where you're trying to make sure that a virtual machine doesn't negatively impact the performance of other virtual machines that are running on the same physical machine. And finally, I worked on infrastructure management, an extensible framework for managing virtual machines and the resources allocated to them. So as I said in this talk, I'll primarily focus on the novel applications and briefly talk about the memory management work, but I'm more than happy to discuss the rest of the projects offline. So with this background and motivation, here's the outline for the rest of my talk. I'll first present a technique called time dilation that allows us to go beyond the capacity of the underlying hardware and show its application in protocol evaluation. I'll then present DieCast, which is a framework that leverages time dilation to do large-scale testing using a much smaller infrastructure. Next, I'll briefly discuss a system called the difference engine that allows for more efficient memory management in virtual machines. And I'll then touch upon some related work before concluding. Now, before I dive into details, I want to take a moment to quickly introduce Xen. So while most of the ideas that I'll present here are applicable to virtual machine monitors in general, the implementation is largely based on Xen, which is an open source virtual machine monitor out of the University of Cambridge. When Xen boots, it starts an initial virtual machine called Domain 0. Domain 0 is sort of the control entry point for the system where you can create and manage other virtual machines. There are two different kinds of virtual machines that are supported in Xen. Para-virtualized virtual machines require modifications to the guest operating system to make them virtualization aware, allowing for some performance optimizations. But the flip side is that you can't support all operating systems. In particular, operating system for which the source code is not available can't be supported. Xen also supports fully virtualized VMs, which allow running unmodified guest operating systems. So you could run Windows, Solaris, whatever have you, but they require hardware support, such as the Intel VT processor. All right, so let's talk about time dilation. Consider this physical machine here with a given configuration, and this physical machine will potentially host several virtual machines. Now, an obvious consequence of doing this kind of multiplexing is that these resources will get split up among these virtual machines. So each virtual machine individually has access to only a fraction of the underlying resources. So in particular, in this example, let's say you create 5 identical VMs, and these VMs have equal access to all the resources, and they have equal amount of work as well. Then each virtual machine roughly sees the equivalent of a fifth of the resources. So it'll see a fifth of the CPU, it'll see 1/5 the network connectivity, and it'll have 1/5 the main memory on the machine. The goal with time dilation is to somehow increase the amount of resources a virtual machine thinks it has. And we'll see how it can be useful as we go along. So here's the idea. What we do is we take time and trade it off for other resources in the system. So consider this example. Over a period of 1 second, let's say the operating system receives 10 megabits of data. If you then ask the operating system what is the bandwidth that it perceives, it's going to say 10 megabits per second. In time dilation, we're going to slow down the passage of time inside the operating system. So let's say if we repeat the same experiment, but this time we convince the operating system that instead of 1 second, only 100 milliseconds have passed. But it still sees the same amount of data. So if you now ask the operating system what is the bandwidth that it perceives, it's going to say 100 megabit per second. So it thinks that it actually has a faster network than it actually does. And so by slowing down the passage of time inside the operating system, we can make all these time-based resources, such as the CPU, the network bandwidth, the disk bandwidth, all appear faster. Of course, now your experiments will take much longer to complete because for each second of real time, only 100 milliseconds are passing inside the operating system's time frame. So we call this ratio of the real time to virtual time the time dilation factor, which in this case is 10. So let's revisit our multiplexing example with time dilation. So earlier we saw that if we have 5 identical VMs, each of them roughly sees a fifth of the underlying resources. Now if we take each of these virtual machines and run them under a time dilation factor of 5, all of these VMs will roughly see 5 times the resources that they had. But note that time dilation only impacts time-based resources, like temporal resources. It doesn't impact static resources such as main memory capacity or secondary storage capacity. So each of the virtual machines still sees 400 megabytes of RAM. And I'll come to this point later again. But note that there's really nothing special about the number 5 here. We could have picked a different time dilation factor, and the perceived resource capacity would change accordingly. So if we picked up time dilation factor of 4, the VMs would perceive a different resource capacity. Now, why did we have to create 5 virtual machines? there's no strong reason to create 5 virtual machines either, right? In particular, I can have a single virtual machine on this physical machine. And so let's say you have some physical machine with a gigabit per second network, and you create a single virtual machine on this physical machine. So originally, this virtual machine has access to the entire gigabit per second of bandwidth that's available from this machine. Now, if we run this VM under a time dilation factor of 10, we can actually make it believe that it has access to a 10 gigabit network. And this is precisely the kind of thing that we need to do the scalable network emulation that I gave an example of earlier in the talk. Are there any questions at this point? All right. So how do we go about implementing time dilation? The general strategy for implementation is that you have an operating system, and that operating system relies on a variety of time sources to infer some value of time. So the most common one is timer interrupts that the operating system is receiving, but there can be several other time sources as well. Right? You could have specialized counters such as the TSC on x86 platforms. There might be other hardware timers such as the high performance event timer or the programmable interrupt timer, and there might be some information maintained in the BIOS as well. And so the challenge here is to basically figure out all the different time sources that an operating system might use. So the operating system takes all these time sources and infers some value of time. So the key point is that the operating system doesn't have any notion of absolute time or real time. And so to implement time dilation, what we need to do is we need to interpose between all these different time sources and scale them appropriately by the given time dilation factor. So it might involve reducing the frequency of the timer interrupts or manipulating the value of the TSC that's visible to the operating system. And if we can interpose between all the different time sources, the operating system will automatically perceive a different value of time. Now the challenge here is that the implementation should be both transparent and pervasive. Now by transparent, what I mean is that we shouldn't have to modify the operating system or the applications to support time dilation because we want to support unmodified operating systems. The implementation should be pervasive in the sense that the operating system and the application should have no way of figuring out that they're running in this dilated time frame. If the real time somehow leaks into the system, then we will see different behavior than expected. Yeah.
When I'm running in a virtual machine, that's getting a tenth of the CPU, I don't see my CPU clock going 10 times slower. I get sudden bursts of it. So if one simple way this would become, unless you're scaling based on the number of CPU cycles I'm getting, this isn't going to be transparent, right?
So you raise a great point. Transparency, absolute transparency is hard to achieve. What we are trying to say is that depending on the application that you're running, it might not matter if the exact distribution of CPU cycles is preserved or not. Right? And so as we'll see later, for most applications, it doesn't really make a difference if the number of sequences. So all we are saying is that in 1 second, so let me retrace. So if you did some CPU intensive task in a regular operating system and you timed it, you will measure it took some amount of time. Right? All we are saying is that under time dilation, if you repeated the same experiment, it will take a tenth. If you were using a time dilation factor of 10, it would take a tenth of the time, simply because that's how you're measuring. Does that make sense? So in that sense, the CPU appears faster. Yeah.
I think that we're all very curious about how you deal with bursty effects of the virtual machine manager's multiplexing.
I'll come to some of it later as I go along. All right. So the implementation that we have for Xen, does roughly the same things that I just described. We scale all of the different time sources by the given time dilation factor. In fact, we allow each virtual machine to be run with a different time dilation factor, which is extremely useful. Our implementation supports both para-virtualized and fully virtualized VMs. Go ahead.
I don't think you use this, but how do you handle the read TSC?
For para-virtualized, for para-virtualized VMs, the argument is that because para-virtualized operating systems anyway require modification, for our para-virtualized implementation, we actually just modify the operating system itself. But if the application, if you're going through the operating system to access the TSC, then we will trap it and return the right value. But in para-virtualized operating systems, the applications might still be able to access the TSC directly by executing assembly instructions in hardware. So you're right. For those applications, you have to do some kind of trap and emulate. So you have to watch the instruction stream that's emanating from the VM and sort of run there. But right now we don't handle that case. No. Any other questions? Okay. I do want to mention here is that you could implement time dilation directly inside the operating system without having to go through this virtual machine interface. But implementing it inside the virtual machine monitor makes this kind of scaling very easy, because you already have interfaces for exposing the different time sources through the virtual machine monitor. So this makes it much easier. But the real issue, as some of you have brought up, is that do we believe time dilation, in particular for these bursty kind of allocations, and what is the impact of multiplexing? So how do we test if time dilation really works? Our general methodology for validation is that we're going to pick some baseline that we can currently attain and validate. We're then going to scale this baseline down. And this scale down can be either in the form of picking a less capable hardware or artificially restraining the resources available to a physical system. So once we have the scaled down system, we are going to use time dilation to scale it back up to get a perceived configuration. And then the goal is to compare the performance of the baseline and the perceived configuration. And if the amount of resources in the perceived configuration are similar to the amount of resources in the baseline, then the expectation is that they should behave similarly. So in the invariance we want to maintain is that of resource equivalence. So basically what I mean by that is that after time dilation, the perceived configuration should have the same resource capacity as the baseline system. So how do we get this scale configuration? Let's start with a simple example here. Here I have a single link, which is running at 10 megabits per second and 20 millisecond of round trip time. And these endpoints might be running under time dilation. And the invariant that we want to preserve in this case is that as perceived by these endpoints, the link should have the same network characteristics all the time. So in the baseline system, which is equivalent to having a time dilation factor of 1, the real and the perceived configuration are exactly identical. Now, if we were to run the endpoints at a time dilation factor of 10 without doing anything else, the endpoints are going to perceive a much shorter latency on the link, in particular 2 milliseconds, and a correspondingly faster bandwidth. So the link will appear to be 100 megabit per second and 2 millisecond link. So what we need to do is we need to artificially scale down the capacity of the link and make it slower, so that after time dilation, the perceived configuration matches the real configuration. And in particular, we want to manipulate the link so that it has actual bandwidth as 1 megabit per second and latency of 200 millisecond. Now we can easily do this kind of manipulation of the link configuration by using a traffic shaping tool at the endpoint or using a network emulation environment to manipulate the characteristics. So note that this also goes back to the pervasiveness argument that I was talking about earlier. To preserve this illusion of time dilation, we want to make sure that all the components involved in a distributed system, the endpoints, each of the links, any appliances you might have in between routers and so on, they should all be scaled uniformly. Otherwise, we will get unexpected behavior. So next week we come to the actual experiments that we do for validation. We have validated time dilation for a wide variety of configurations, but it's really easy to match coarse-grained metrics like aggregate throughput over some period of time. And what we really want to see is how does time dilation behave on very, very fine time granularities. So let's start with this simple experiment. Here we have a single TCP flow, and we inject 1% deterministic losses in this TCP flow. It's going across a 100 megabit per second link with a round trip time of 20 millisecond. And we're looking at the first second of trace. So on the x-axis, you have time since the beginning of the experiment. On the y-axis, you have the sequence numbers. And basically, this is showing a packet sequence diagram of the first second of trace. What we want to do is we want to repeat this experiment under different time dilation factors, making sure that the perceived link characteristics remain the same. And then we want to see if we can preserve this low-level packet behavior. Right, so here's the baseline configuration again at the very top. We repeat this experiment at a TDF, time dilation factor of 10, again making sure that the perceived configuration is the same at a time dilation factor of 100. And visually, you can see that the traces look very, very similar. Of course, we've also done statistical comparison by using the distribution of the inter-packet arrival times and so on. And even those distributions match. And so for this very simple case, time dilation is able to preserve low-level packet behavior. But this is, again, a simple case with a single flow. We have also validated time dilation in more complicated scenarios where we have multiple flows, varying bandwidths, varying latencies, and so on. And I'm not going to present the details here, but for all of these validation experiments, we show that time dilation can actually preserve the baseline configuration. And coming back to the point you had about burstiness behavior, again, I think it goes back to what is the fidelity of your implementation? If the time sources that are being used by the application, by the operating system, are all the time sources that you have already interposed on, then no matter what granularity the application tries to get a value of time, it will get the scale value of time. So the only case where burstiness actually will show through is when the application is using a time source that we cannot capture, which is what Ed was pointing out. So in the para-virtualized case, if you have applications that are directly issuing assembly instructions to read the TSC value, that's something we do not handle right now. Yeah.
But there are implicit ways that the time can affect you without measuring it. Like, the burst example, if the two slowed down machines are on different VMs, then they can interact at a fine grain. And if they're on the same VM, one of them might get to run for some long quanta and not see a response from the other one until the end of that quanta. And that's something that you're not slowing down anymore.
That's a great point. So I think what you're pointing out is that there is some overhead involved in doing this kind of multiplexing.
I'm not talking about overhead. I'm talking about the bursty and the quantization of the CPUs. For example, you could do time dilation, wherein you gave each VM a 10-second quanta, and the first VM would spend its 10 seconds perceiving it to be 100 seconds and wondering where the heck that other guy went, right? And then we switch to the other guy, and he wonders what he timed.
So again, so most of the workloads that you can see here, for network I/O, it's not going to happen, right? Because you're going to send some packet, you're going to wait for some response, you're going to block, and then the context switch will happen, right? And so you're not ever going to run for 10 seconds straight.
Not if you're. My point is, if you had enough to do, and your machine and your infrastructure were very foolish and allocated these 10-second quanta, then you absolutely would see an effect in the network. So you can counter by saying, oh, but we don't use a quanta that's that big. How do we know yours is small enough or fidelity enough?
Right, sure. So one of the things we do is we modify the scheduler that the virtual machine monitor uses to use much smaller time quanta. So you can, you make sure that no virtual machine is running for too long and trying to break the solution. But again,
how do you know, I guess is the question. How small is enough?
That's a great question, and our metric has been to try different kinds of applications that we care about and see if we can preserve their behavior. For all the application-specific performance metrics that you might want to measure. And for the applications, this is just one class of application that I'm talking about, but later on I'll talk about several other classes of applications, and for all those, it hasn't mattered. And so you're right that there might be some artifacts that we're not able to capture, but if the applications that you're using are not concerned about them, then how does it make a difference?
So what observation would have falsified your hypothesis back when you were showing us those graphs that sort of visually matched?
Mm-hmm.
Did you have, what's your test for not matching enough? Like if I had built a competing system that would also attempt to achieve the same goal, but get some egregious error, what would be a characteristic of my graph that, did you ever see a graph that you looked at and said, oh, that isn't faithful enough?
I'll come to that later. So there are artifacts in the system where you have to do additional work to make sure that the graphs do match. But basically our metric has always been pick an application, whatever application, we don't care, and look at the metrics that you normally use to measure the performance of that application, and then run it under time dilation and see if you can match that performance. And if there were a finer grained metric that you wanted to use, you look at that and see if you can match it. Okay. So as I said earlier, in a distributed system, you want to make sure that all.
But if you run in bursts, so your clock goes fast and then stops and fast and then stops, NTP is not going to work very well.
So in the frame in this environment, we're basically, if you're using NTP, the NTP server has to be running in the dilated time frame as well, because.
Of course, it has to be running in the time frame, but if time goes fast and then stops and fast and then stops, and they're not in lockstep across all the machines, then NTP isn't going to converge properly. I know I've actually run it on machines that had clocks that did that because the clock was busted, and it doesn't work.
So I've never experimented with NTP, so I really don't know the authoritative answer there. Yeah.
So when we were
talking about Amazon or something else. Have you reasoned about DiscIO?
We have. I'll come to that in a bit. All right, so let me move on, and I want to talk about one of the examples of time dilation. So again, coming back to the protocol evaluation example that I had earlier. So in the Linux 2.6 kernel, the default flavor of TCP is TCP Nureno, but Linux also ships with this another variant called TCP BIC, which stands for binary increased congestion, and this variant features an enhanced congestion control protocol designed specifically for high bandwidth networks. And what we want to do is compare Nureno versus BIC on high bandwidth links and see which one does better. So the goal here is to treat these protocols as black boxes. We're not trying to reason about the behavior that we see. We're just trying to see, can we use time dilation to push beyond the hardware limit and uncover interesting behavior. In particular, does BIC really outperform Reno as you increase the bandwidth? And so here's the experiment setup. We have a single bottleneck link, and we have 50 TCP flows that are going across this bottleneck. We're going to fix the round trip time of the bottleneck link to 80 milliseconds, and we're going to vary the bandwidth on this link. And for each value of bandwidth, we want to measure the per flow throughput that we see. So in the first sort of phase of the experiment, on the x-axis, I have the bandwidth of the bottleneck link going from 0 to 1 gigabit per second. On the y-axis, I have the per flow throughput in megabits per second. Now, the first thing to note is that in this range, because we have gigabit hardware in our cluster, we can actually simply run the real operating system without using time dilation and measure what the performance looks like. And so the blue dots here are the performance with regular Linux, no time dilation. Then we can repeat the same experiment just to validate if our setup is correct. So we repeat the same experiment using a time dilation factor of 10, again making sure that the perceived bandwidth remains the same in each case. And the green triangles are the performance under time dilation. And in this range, you can see that they match. They're within the variance. The performance is very close to what we see in the baseline. The red squares are the performance we get with TCP BIC, and in this range, there is no clear difference between the performance of these two different TCP variants. But because we are using a time dilation factor of 10 and we have a gigabit hardware at our disposal, we can actually push further and test up to 10 gigabits per second.
So you didn't do BIC with a TDF of 1?
We have, but it's not on this graph.
What's it look like, roughly?
Yes, it's the same. Yeah. So in this range, we are pushing up to 10 gigabit per second. Again, on the y-axis, we have the per flow throughput. And here we see that as we increase the bandwidth of the bottleneck link, TCP BIC begins to outperform TCP Nureno. So definitely, there seems to be some advantages that BIC brings to the table. But does it continue to outperform Nureno if we push even further? So we can actually use a higher time dilation factor to test at even higher bandwidths. And so we move to a time dilation factor of 100 that allows us to go up to 100 gigabit per second on the bottleneck link. And there are two interesting things in this graph. The first is that the performance of both TCP BIC and Nureno sort of flatten out, so they don't increase in terms of the bandwidth that they can extract on this link. And secondly, the performance differential between these two variants seems to shrink in this range. And so the claim here is that TCP BIC is good for high bandwidth networks, but only up to a certain range. And after that, we hit a point of diminishing returns where TCP BIC doesn't prove to be as beneficial.
But wait.
Yeah.
From the same series of data, I can also draw a completely different conclusion. You have to finish and distinguish between them. I can back up 2 slides and say at the small range, we have verified that through the time dilation filter, these things look the same. And as we can see on the next slide, at some point, the time dilation filter seems to see something that's different, but then on the third slide, it looks like we can't tell the difference anymore. Like we can't actually tell whether the phenomenon that we see past the validated area is a function of the variance between, or the difference between Nureno and BIC, or a function, or a limitation in the fidelity of it. I mean, it seems like you're trying to simultaneously validate the mechanism and draw a conclusion from it. You can't do both of those at the same time.
That's a great point. And the whole point of, we spend a lot of time in this project just trying to validate. And we can only validate, up to the sort of the hardware capacity that we have. And so in this case, we had gigabit hardware, so we validated up to a gigabit hardware. And beyond that, it is our hope that once we can actually test on 100 gigabit per second networks, it will look something like this, but we have no way of finding out right now.
People run NS simulations for this. Did their results look like yours?
We did look at NS results for some of the things, but not this particular experiment because NS didn't have an implementation of TCP BIC and so on. So, I mean, the problem with doing a apples to apples comparison with an experiment like this in NS2 is that, I mean, you don't have the real operating system stack. I mean, there are so many other artifacts that are different there.
I realize, but if you got a result that looked like what NS did, at least qualitatively, then that would lead you to believe that.
So we've done it for some other experiments, but not this one.
And it may be that they're wrong, or it may be that you're wrong, or maybe that they're wrong. But
sure. So we haven't looked at NS2 results for this experiment, but we have for other experiments. Yeah.
As you're scaling up the bottleneck bandwidth, are you scaling up anything else? And I'm wondering if the bottleneck remains the bottleneck as the bandwidth.
So I'm not sure what you mean by that. So I mean, like
Are the endpoints getting faster? Do they get more CPU?
Yeah, so the endpoints are running at time dilation factor of 10, so they do have more CPU in that sense, yeah. Oh, actually,
so the error bars are going to be really big here. I assume that's because it takes so long to run the experiment. You can only run it 1.5 times instead of 10. Or
well, so these error bars are across the 50 flows. They are not across different runs. So, I'm plotting the mean and the standard deviation across those 50 flows. Yeah.
Do you suppose that those errors, those bars are getting bigger because of the behavior of the protocol, or are they getting bigger because burstiness is now starting to hurt you more and more?
Again, I don't know for sure. I mean, in the range that we validated, it didn't look like we were adding something to the error bars. But in this range, I don't know for sure. All right, so I'm going to move on at this point. And the takeaway here is that we think that time dilation can be used as an effective tool to push beyond hardware limitations to do this kind of protocol evaluation. And I think compared to the current state of the art in terms of the techniques and the tools that you have available, I think time dilation gives you more realism and accuracy at the same time. So that's just one application. There are several other applications you could use time dilation for. You can use it to predict how performance of your cluster will change if you upgrade some piece of equipment. You could also explore how the bottlenecks in your application evolve as you give it more and more resources. But there are certain limitations to be kept in mind when you're using time dilation. First of all, time dilation doesn't scale static memory capacity, as I mentioned earlier. And our work on difference engine addresses some of the issues here, and I'll talk about it towards the end of the talk if I have time. But remember that for pervasiveness, we want that everything in a distributed system is running under the same time dilation factor. And if you have some specialized hardware appliances that either cannot be virtualized for some reason, or if the firmware on the appliance is not accessible for a direct implementation, then these need to be dealt with differently as a special case. And finally, time dilation cannot capture radical hardware changes. So if 100 gigabit hardware looks fundamentally different than how we construct a gigabit hardware, then the accuracy of the predictions that time dilation makes will degrade. And so we can't capture all the technological evolution. Yeah?
So to what extent is the limitation the amount of sort of higher level coordination between nodes in a complex distributed system?
So, one of the motivations is, we want to simulate Amazon or something like that, right? Well, like in Bill's example, with the NTP, there's actually sort of interesting higher level synchronization that your system doesn't necessarily capture, right? So the evaluation you showed us here was basically bulk TCP throughput, right, which is fairly straightforward. But I mean, at what point do you have to say, okay, the system we're trying to emulate is so complex, we have to somehow intuit about global synchronization behaviors, or things like that?
Right. So in this work that I'm going to talk about, DieCast, I'll present evaluations for much more complex distributed systems. So hopefully that'll address your point. Yeah.
Does TCP Reno look at the time, saying the latency is 10 milliseconds, I'm going to do something differently, or if it's say milliseconds?
Excuse me, I didn't get that.
Does TCP Reno take latency into account?
Yeah.
Yeah.
It does. The actual number, if you feel the C is at a millisecond, the do things different when C is at a okay.
All right. So next I'm going to talk about DieCast, and just to refresh, the motivation here is to use a small infrastructure to test a much larger system. And we want to do this kind of replication and testing with some goals in mind. The first thing we want is fidelity, right? We want to make sure that we can replicate the original system to as great a fidelity as we can. We also want reproducibility in the sense that we want to be able to do controlled experiments, for performance isolation, for performance debugging, and so on. And finally, we want to be efficient in the sense that we want to use as few resources as possible to do this replication and testing. And as I said before, I'll show that DieCast can scale up a given test infrastructure by an order of magnitude or more. So let me walk you through the approach that we take with an example. So here we have a typical 3-tier web service. We have some web servers. We have application servers. We have database servers. They're all connected with through some high-speed fabric. And then we have a load balancer in front of the system. And the goal now is to replicate and test the system using fewer number of machines. Now note that if you were to make a complete exact copy of the system, you would get fidelity because it's basically the same system all over again. And you might also get reproducibility. But by our definition of efficiency, because we're using double the resources, the system is not efficient. So in order to bring efficiency back, what we do is we're going to encapsulate each of these physical machines into virtual machines, and then we're going to consolidate these virtual machines on a fewer number of physical machines. So we do server consolidation that gives us fewer number of physical machines, but now we've lost the original topology of the network. So we're also going to put in a network emulation environment that can recreate the original topology. But now we have the problem that each of these virtual machines only has access to a fraction of the resources of the underlying test machine. And furthermore, the machines in the test harness might be completely different than the machines in the physical machines in the original system. So we have lost fidelity. So how do we reconcile fidelity? So let's see what we want to do here. So we have some machine in the test harness, and here we have some physical machine in the original system. Now so far what we have done is we have created some number of virtual machines on this test machine. And what we want to do is we want to take one of these VMs and make it look like the corresponding physical machine in the original system. So obviously one of the things that we need to do is we're going to use time dilation to scale up the resource capacity that's visible to this VM. But the other thing we need to do is that to take into account the heterogeneity between the machines in the test harness and the machines in the physical system, and also because each of these virtual machines might not be identical, they might be configured differently, we have to be able to precisely control the amount of resources that are available to this virtual machine. So in particular, the amount of CPU that's available to it, the amount of network that's available to it, and the amount of disk that's available to it. So for the network scaling, we use traffic shaping tools in combination with network emulators, as I described earlier. For CPU scaling, we leverage CPU schedulers inside the virtual machine monitor. So we can say things like this virtual machine should get 10% of the CPU. There are some subtleties involved in the CPU scheduler, but I don't have time to cover them now. But for the most part, we just leverage existing CPU schedulers. But what about disk I/O? Under time dilation, the disk will appear to be much faster, and in particular, it can be perceived as a completely different disk than the disk in the original system. And we want to make sure that the VM sees the same disk as the physical machine sees in the original system. So how do we deal with disk I/O scaling? So before I describe that, let's just first look at how disk I/O happens in Xen. So again, here we have implementations for both para-virtualized and fully virtualized VMs. But in this talk, I'm only going to talk about the fully virtualized implementation. So here we have an unmodified operating system. It thinks it's using a real disk drive. So the device driver is unaware that a real disk doesn't exist. Now in practice, the file system of the VM might be backed by a disk image or a partition in domain 0. There is a user space process in domain 0 called the IOEMU, which is responsible for doing the IO emulation for this particular VM. So any disk requests that originate inside the virtual machine will be intercepted by the IO emulator process, which will then do the operation on the virtual machine's behalf. So access the hardware, do the read, write, and so on. So this is the model that we're working on. So what is the goal? Again, so the goal is that we want to preserve the perceived disk characteristics. So everything from seek times to disk throughput and so on. And because the disk will appear faster under time dilation, what we want to do is take each request and slow it down by some amount to make sure that inside the virtual machine, the perceived characteristics remain the same. Now the challenge is that a lot of the low-level functionality for disk resides in the firmware, and so the firmware might do batching and reordering of requests for efficiency, masking some of the delays. But the bigger problem is that the test harness may have a completely different hard drive than a physical machine in the original system. And so, how do we reconcile these two completely different pieces of hardware? So our approach to addressing both these issues is to use DiskSim. DiskSim is a high-fidelity full disk system simulator out of CMU. So what DiskSim does is that you give it a model of a disk to simulate, and then for each request, it will report how long would the request take to service in that particular disk. So we have DiskSim running as a separate user process, and what we do is for each request that comes to IOEMU, we forward the request to DiskSim. So DiskSim knows things like which sector number is being accessed, what is the size of the request, what is the type of the request, read, write, and so on. And after that, it will return the service time in the simulated disk. Do you have a question?
I have a question related to this. My understanding is if everything is like, if those VMs, you can divide the CPU or the network bandwidth evenly, right? It's okay. But in disk, there's a queue model, right? If everyone share a same queue, then it's hard to make sure everyone gets like the distribution or the split of the time evenly. How do you solve that problem?
So that's a great point, and which is precisely the reason we want to control the time it takes for each request to service, right? So in particular, DiskSim is going to return the service time in the simulated disk. And we know the time dilation factor. We also know how long the request actually took to service inside IOEMU. Based on these, we can figure out how much to delay each request by before you return to the virtual machine. And so you can precisely configure, precisely control the time that the virtual machine thinks the request took to serve. And so the illusion that we are trying to preserve is that the virtual machine is actually talking with the simulated disk and not the real disk. Yeah.
I think you're running on multiprocessor systems, right?
We are for some of the experiments, yeah.
For some of them.
Mm-hmm.
Because the disks, you've still blown out of the water your disk sequential I/O. You've got multiple.
So
I mean, are you confident? DiskSim is emulating a single machine to a single disk. And how are you reasoning about multiplexing, DiskSim with all these different requests?
So
wanting to emulate an individual disk on an individual machine.
So part of the reason why it works is that under time dilation, each request actually has more real time to finish. So even if there's some overhead in running multiple DiskSim processes and so on, because you have more time to finish, we can still do this kind of emulation without breaking fidelity.
So one thing that could happen, I think what Ed was pointing out, is that you could have, if all of your multiplex processes were doing sequential I/O, and you start now time slicing between them, you might see a slowdown. If the quants are small, which we need for fidelity, we might see what looks like a random I/O to the real disk, and that can slow down by much more than an order of magnitude. So do you actually validate that DiskSim says I want this request to arrive at this time. Do you validate that you aren't often late?
So for DiskSim, the validations that we have done, we used some standard file system benchmarks like dbench and IOZone, and whatever the access patterns they use are. We didn't specifically try a benchmark that only had random IOs.
I think you're misunderstanding. If you had 10 virtualized machines, 10 virtual machines,
mm-hmm.
all of which were doing sequential I/O,
mm-hmm.
but together, effectively doing.
So we haven't done that exact experiments, but I will talk about experiments where we have a bunch of virtual machines who are doing a bunch of disk I/O. We're not sure if that's exactly sequential, but for those experiments, it hasn't been an issue.
Look,
but I can imagine that you could.
Another question.
Mm-hmm.
You could leave running all the time. If I were to have built this, I would have said, assert that the time DiskSim said to return the request is after the time I actually got the request.
Oh.
And measure how often that was.
Yeah. So you're saying that what if the amount of time we actually want to delay is like negative, right? That right. DiskSim has already taken long enough that you're right. So
no, the actual disk has taken longer.
Yeah. Yes. So in the system, we actually have checks for that. In the experiments we have, it doesn't happen. No, it doesn't happen often. So it happens like very, very rarely. I don't have the exact numbers for it, but we do have checks for that. and we don't explicitly deal with it anyway. So one of the things we tried doing was to sort of accumulate this negative time and incorporate it in a later request where we have enough buffer. So we played around with some of those, but in the experiments so far, it hasn't mattered. All right, so the impact of all this is that the virtual machine thinks that it's interacting with the simulated disk, which we can choose to our own liking. So by doing this, we can preserve the disk I/O characteristics as well. So far the approach has been that we're going to multiplex VMs for efficiency. We're going to use time dilation to scale up the capacity of each VM, and we're going to use independent knobs on the CPU, the disk, and the network to make sure that each VM has resources exactly equal to the corresponding physical machine in the original system. And the claim after doing all this is that the scale system almost looks like the original system. I say almost because we still don't deal with things like the main memory capacity, and I'll talk about it later. So how do we validate DieCast? Well, the same methodology as before. We set up a baseline system. In the experiments that I'm going to talk about, the baseline is 40 physical machines running a single VM each. And for the DieCast scale configurations, we have 4 physical machines running 10 virtual machines each with a time dilation factor of 10. And then we want to compare the performance of these two systems. And the questions we want to ask is, A, can we match application-specific performance metrics? And B, can we match low-level system behavior like the CPU utilization profile as a function of time? So we validated DieCast on a variety of systems. In this talk, I'm going to talk about one of the systems. This is a service called RUBIS. It's an e-commerce system modeled after eBay. So you have some web servers and database servers. In this experiment, we are modeling 2 geographically distinct sites, so they're connected by a wide area link. And the servers, half the servers in each site talk to the database servers on the other site. The nice thing about RUBIS is it comes with a configurable workload generator. So you tell the workload generator how many user sessions to simulate. Yeah.
Why did you choose this topology?
I mean, just something we came up with. There's no strong reason.
This is the only topology you tested?
We have other topologies for RUBIS in the paper. This is the only one we have. But we have different topologies for BitTorrent. We have different topologies for the third system that we tried out.
It's just unusual. So I was just curious.
Yeah, no. I mean, we just wanted to make sure there is moderate, there's reasonable complexity that, communication is happening both within each site, across sites. We are exercising local area links, wide area links, and so on. So it's just something that we came up with. So we have one workload generator for each web server, and we increase the workload on the system and see how it behaves. So the workload generator that RUBIS comes with, it reports a bunch of metrics at the end of the run. These are, again, application-specific metrics that the workload generator reports. We do nothing to them. And so the first thing we're going to do is we're going to compare the metrics in the DieCast system versus the baseline. So on the x-axis, I have the total system load in terms of the number of simulated user sessions across all the machines. On the y-axis, I have the aggregate throughput of the system in terms of requests per minute. The solid red line is the performance of the baseline configuration, and the dashed cyan line is the performance of DieCast. And you can see that at least for this metric, they almost perfectly overlap. I'm also showing a third line here, which is labeled as no DieCast. And this basically is that if you were to just multiplex VMs without doing time dilation or any other kind of scaling, this is the performance you would get. And as you can see, if you are not using DieCast, the performance differential, the system diverges significantly from the baseline. And in fact, even more prominent if you look at response time. So on the y-axis here, I have the average response time taken across all the requests. And again, we match the baseline configuration pretty closely. But if you're not using DieCast, the response time degrades significantly because now the virtual machines are running out of resources. Yeah.
Your y-axes are being measured in real time versus DieCast.
No. So we just take the numbers that the workload generator reports to us. The workload generator is also running in this dilated time frame. Right. Mm-hmm.
Backup slide.
Excuse me?
So this says that when you use a tenth of the machines with no DieCast, you get somewhere near half the performance. So that suggests that you didn't really push this far enough, right? Because I'd expect to see something like a tenth of the performance.
It depends on the workload, right? Not always.
That's why it depends on the workload, and I'm suggesting that you probably should have pushed the workload about a factor of 5 farther out, because you didn't really stress the difference between.
Probably, I mean, this is as far as we went, but there are other workloads where.
Maybe I'm not making my point certainly enough. You're telling me, look, these two lines coincide, so we've done a good job preserving fidelity, but the counter that seems to be, but that's because the machine, one possible explanation is we didn't come anywhere close to loading the machines. And the point of having 40 machines is that we're going to load them. And the machines are underloaded by a factor of 5.
So, as I said, we have done other experiments where we do actually push the machines, just not in this experiment. So rephrasing your question, I think what you're saying is that for this application, if you were not to use time dilation, we're not so terribly off from the baseline, right?
No,
and so
I'm not saying that no DieCast is bad. I'm saying the fact that the magenta line and the cyan line agree tells us almost nothing, because we have not.
So you're not measuring the interesting part of the graph.
Right, because there's a lot of
further
variable
out.
time in there.
So, right. So I think I have the graphs in some of the backup slides, but there are. One of the problems we had was that the system was configurable only in certain aspects. So we actually wrote a third service. Let me back up. So we wrote a service where you could configure the amount of computation, communication, and I/O overhead on a per request basis. And there we basically try to push the system in each of the 3 different dimensions and see where we try to break down. And those graphs are in the paper. All right, so this was the application-specific performance metrics, but what about the resource utilizations? So in this system, we had 3 different types of machines: the web server, the database server, and the workload generator. And so what we did was we randomly picked one machine of each type and looked at the CPU utilization. So on the x-axis, you have the time since the beginning of the experiment. On the y-axis, you have the percentage CPU used, and we looked at the compared with the CPU utilizations in the corresponding virtual machine. And the takeaway from this graph is that the utilization profiles are similar. I mean, obviously, we can't match the instantaneous profiles exactly, but they display similar behavior. We do the same thing for memory. I just want to point out that even though we don't scale memory, in this experiment, we had set things up such that the baseline system had the same amount of memory that each of our virtual machines would have, so that we can actually look at the memory profiles. And we also looked at the network. So we looked at each hop in the topology and measured how much data that was transferred on the hop. Of course, this is a fairly coarse-grained metric for this experiment. We sorted the hops by the amount of data that was transferred on them, and then considered the hops in the same order in the DieCast topology. And again, the amount of data transferred seems to match. So as I was saying earlier,
So from the fact that each of these graphs agree, we conclude that the system preserved fidelity.
Yes, for this experiment.
Except that memory was the thing where you didn't even try to preserve fidelity. So you got,
No, so fidelity here is in the sense that if your baseline had the same amount of memory as your virtual machine, does it get utilized in the same way? Right, that's all we're saying. We are not trying to address the fact here that the baseline could have had a lot more memory. Right, that's a separate problem, and I'll talk about it later.
Oh, because you downgraded the baseline.
Yes. Yeah. All right. So we have tested DieCast on BitTorrent, and we wrote this custom service where we exercise different dimensions of the system. And for example, when we have extremely high CPU, we try to see some divergence in the baseline. But for the most part, we can match both the application-specific performance metrics and the resource utilization profiles. But again, these experiments were encouraging, interesting in their own right, but we really wanted to see if you could use DieCast on a real-world system. Yeah.
So how important was it that you used disim, this super accurate thing? If you'd just written a 100-line Perl script that kind of, if it's sequential, how well would that have done?
So we do have something like that for a paravirtualized case, where we don't have such a high fidelity handle on how each requests are going. So there we basically modify the device driver to say, interpose some delay to make sure it works reasonably well. But we use disim because we want to say, we want to use the most fidelity model that we have, the highest fidelity model we had. Where again, the argument is.
Where the graphs go. What is it?
Oh, so it depends on the workload. You can get workloads where the model tries to show leaks. Yeah, but we can talk about it later. All right, so we were really fortunate to be able to work with this company, Panasys. They build high-performance file systems. It's a company based out of Pittsburgh. Garth Gibson from CMU involved in the company. And this is exactly the motivation that I was presenting earlier. They have this problem that they ship their file system to clients which have thousands of machines, but they don't have the infrastructure to test at that scale. And so we wanted to see if we could use DieCast to alleviate some of their testing problems. So their typical testing infrastructure looks something like this. They have a storage cluster which serves the file system. They have some clients that are generating the workload, and then you have connected by some network. So in order to test or run DieCast on this system, the clients are fairly easy to deal with because they just run regular Linux, and so we could use our current DieCast implementation to scale the clients. But the storage cluster was more of a problem because they run their own custom operating system on the storage cluster, and it's tightly integrated with their hardware. And the upshot of all that is that it's not virtualizable. And so we weren't able to use our Xen-based implementation for the storage cluster. So we had to do a direct implementation inside their operating system. Excuse me. And while it was a great learning experience, it would have been much easier if the system had been virtualized, and then we wouldn't have to do much. For the network scaling, we used a standard traffic shaper called DummyNet that their system ships with. All right, so the first thing we did was, again, validation. We set up a storage cluster with 10 clients generating the workload. To test the system, our DieCast scale system sets up a storage cluster with only 10% of the resources, and then we have a single physical machines running 10 virtual machines generating the workload.
Is this all TCP traffic?
I don't recall what protocol their system uses. I don't remember. Yeah. And then we picked two standard benchmarks from their regular test suite, IOZone and MPI-IO. And for each of these benchmarks, we ran their test suite for varying block sizes, and we looked at the metrics that they normally look at, which is, I think, the read and write throughputs. And for each of these benchmarks, we were able to match the performance metrics. But the more interesting part from our perspective is that we were able to use 100 machines in their infrastructure to scale up to 1,000 clients. And before DieCast, Panasys had no way to test things at that scale because they just don't have 1,000 machines to work with.
So does Panasys usually have only one server at all these sites?
Oh, so the storage cluster, I mean, this server has many servers internally. So it actually has, I think 10 or 11 blades running inside, and then they scale it as the demand increases.
And they couldn't scale to 1,000 clients by running workflow generators instead of running?
No, that's what I'm saying. They didn't have 1,000 machines to run the workload on.
You need 1,000 machines just to generate requests on a network, right?
So the way their system is set up, they did require each workload.
Block requests.
No, that's fine. But I'm just saying that.
Are you scaling the servers?
Excuse me?
He is scaling the server. He said that, right? He modified the custom models, therefore he's scaling the servers.
So we do scale the server down before testing it for the validation. And for this one, we do scale the server up, if that's your question. Okay, I'm going to quickly try to talk about some of the interesting aspects of different engines. So memory was a big issue here in trying to create more and more virtual machines on the same physical machine. And this is important, for server consolidation as well. But even otherwise, if you could do with lesser memory the same number of things, then you have incentive to do so because memory is expensive. It's difficult to upgrade and provision a system with more memory, and memory consumes a lot of power. And as move towards multi-core systems, the primary bottleneck in creating more and more VMs on the same physical machine is going to be memory. And so we wanted to consider this problem. Go ahead.
Well, is memory capacity not scaling the same as transistor capacity for doing multi-core?
It might be, but for example, if you have limited number of slots on your motherboard, and the CPU can be multiplexed among several VMs, memory can't be multiplexed that way. So it's simply a fact that it's a static resource and not a time-based resource.
Just asking about the last bullet.
Yeah. Okay. And actually, there's more compelling reasons here because if you can, for example, have the same number of VMs consuming less memory, you can actually turn off selectively, one particular DIMM or something, and so you can save more power that way. So there's incentive there as well. The state of the art in virtual machine memory management is what is called content-based page sharing. This is done by VMware ESX Server and potentially other systems. And the idea is that you're going to walk through memory across all the virtual machines, identify all the pages that are exactly the same, and then for those pages you can do copy and write sharing, which gets you some savings. But the key premise here is that there's a significant potential for savings beyond whole pages. So if you look at sub-page granularity, you can actually extract a lot more savings, and which is what we wanted to do in this work. So just to highlight some of the mechanisms we use, here's an example. We have 2 virtual machines with a total of 5 pages that are initially backed by 5 physical pages. Now 2 of these pages are exactly identical, and 2 of the pages, they're similar but not quite identical, so there are small differences. So the first thing the difference engine does is it shares the identical pages exactly like how VMware and other systems do. So that saves us 1 physical page. The next thing we do is we identify pages that are similar but not quite identical, and for these similar pages, we can store this page as a diff or a patch against the base page. Now the interesting thing to note here is that patch pages have to be reconstructed even on a read access, which is not the case for copy and write pages. The reads there are essentially free. The third thing we do is we identify pages that are not being accessed frequently. And so let's say the blue page in this example is not being accessed frequently. We're going to compress this page and store it compressed in memory. As before, access to compressed pages have to be uncompressed on each axis. And so by using these 3 mechanisms, we can save a lot more memory than the current state of the art. And there are several engineering challenges that are involved in making the system work efficiently. In particular, how do you pick which pages to patch, which pages to compress, which pages to share? How do you identify similar pages efficiently and also accommodating for the fact that page contents might be evolving over time? There is an issue with Xen in particular that the size of the heap that's available to the hypervisor, it's fairly small, and so we have to be careful in the data structures we use and the bookkeeping that we do. And finally, the whole point of doing this memory saving is that you want to create additional VMs, and so at some point you might just run out of physical memory. So we need some kind of memory over commitment support for demand paging things out to disk. And so we had to build this as well for Xen. And I'd love to talk about the implementation later on. And for now, I just want to summarize the results of our evaluation. We demonstrate significant savings not just for homogeneous workloads, where every VM is running the same operating system, same applications. We also demonstrate significant savings for heterogeneous workloads, where you have different operating systems and applications. And we can extract up to twice the savings from VMware ESX server in head-to-head comparisons. And in all the cases, we see less than 7% degradation in application performance. And we actually show that we can use the additional virtual machines to increase the aggregate system performance. Now let me quickly wrap up here with some related work. The literature is rich in all these areas, so I'm just going to highlight a few of the things. As I mentioned before, simulators such as NS2 are great, but they're great for extrapolating beyond some hardware capacity, but at the cost of realism. And on the other hand, emulators such as ModelNet give you realism, but you are still fundamentally limited by the capacity of the underlying network. And time dilation sort of allows you to get the best of both worlds. With respect to testing large-scale systems, the shrink work in Infocom 2003, I think, is closest in spirit to DieCast. And their scaling hypothesis is that under certain assumptions, you can take a sample of the input traffic and use it to extrapolate traffic in a bigger network. But shrink only captures network-based systems, whereas DieCast is able to capture end-to-end characteristics of a distributed system. You could also use test beds such as PlanetLab or EmuLab to do large-scale testing, but again, you're still fundamentally limited by the number of machines that you have in the system. And finally, in terms of memory management for virtual machines, ESX server does a great first step by using content-based page sharing, but we demonstrate that there are actually a lot more potential for savings if you look at sub-page granularities. And we leverage work in compression algorithms for main memory. So when we're compressing pages, we don't use general purpose compression algorithms like the Zivilempo compression, but there are specialized compression algorithms that exploit the fact that memory has some structure to it. So typically you'd have numbers stored in memory, for example, so you have some 4-byte granularity. And so it exploits that kind of structure to do better compression. We leverage previous work in this area. So just to briefly mention some future work. our current implementation for DieCast doesn't scale low-level subsystems. So for example, under time dilation, things like the PCI bus or the memory bus will still appear faster. Now, for most of the applications, such low-level subsystems don't make a difference. But if you have an application that's extremely sensitive to memory access latency, and in particular, if the access latency decreases and you see some performance degradation, then this will be a problem. Interposing on each memory access in software is prohibitive, but the hope is that with better hardware support for virtualization, this is something that we can deal with moving forward. I've also done work on infrastructure management of virtual machines, and the initial placement and subsequent migration of virtual machines is a topic that I'm interested in. In particular, I'm looking at building power-aware policies for placement and migration without the need for expensive instrumentation and sensors in the hardware. And also for a system like Difference Engine, we want to be able to place virtual machines that are similar in contents of their memory on the same physical machine. And so I'm looking into this work as well. And the challenge here is to come up with compact representations of the contents of a virtual machine's memory and efficiently compare these representations. And so we're building some algorithms based on min-wise hashing to do this. And finally, another way that we might address memory capacity under time dilation is to use fast secondary storage devices like SSDs to supplement main memory. So under a high enough time dilation factor, the really fast SSDs can actually appear as fast as main memory. And so this is something that I'm just starting to look at right now. So in conclusion, the general theme of my research has been, as I said before, to make virtualization more scalable, both for supporting existing applications like server consolidation, but also in terms of enabling new classes of applications by pushing beyond the limits of the hardware. So this kind of scalable multiplexing poses several challenges, and I've addressed some of them in my work, but also opens up several opportunities. And I gave you two examples of the kinds of problems we can use virtual machines for. All of the source code for these projects is available online, linked through my webpage. And thank you for listening. I'm happy to take questions at this point.
So I was wondering if you have specific examples of distributed systems where you think this isn't necessarily the best approach. Because, I mean, what if I propose that maybe this system is good for systems in which it's mainly TCP based, it's fairly well delineated between uploaders and downloaders, right? And so you've showed that you can preserve certain TCP semantics, for instance. But I mean, in what type of scenario would this just blow up? So, what if, like BFT, or what about like an overlay or something like that? I mean, I'm wondering at what to what extent there's a little bit of overhead or fuzz in terms of scheduling and things like that. What you've shown is that, okay, for some TCP scenarios, that's fine. But under what timing instances or synchronizations do you think that would fall apart?
So I think disk is certainly one of the biggest concerns that we have. The workloads that we have looked at so far have been okay, but we haven't really stressed the system in terms of, for example, every VM is running a database-intensive benchmark like TPCC or TPCC W or something. And I think that for those kind of workloads, we will start to see some deviation from the baseline. So I think disk is sort of the thing. I'm not that concerned about the network because I think the network is much easier to scale than the disk is. Because again, realize that under time dilation you have more time to finish an operation, and so with virtual machines in particular, and with Xen even more so, the overhead for multiplexing things when the virtual machines are doing disk I/O is much higher than when they're doing network I/O, and so I think that is where the system will start.
I'm just saying that just emulating, the network in itself may not be enough if there are complicated timing things that are going on, right? So you can accurately model, say a bunch of bulk TCP flows, but some of these scheduling issues that came up become more important. Then that doesn't make as much of a difference, right? So like if host availability fluctuates a lot, or there's some type of complex message passing protocol, it seems like there might be complexities that haven't been explored yet.
So I mean, we've looked at peer-to-peer networks like BitTorrent, and we've set up our own topologies. So for those, it seemed to have worked. I really don't know what kind of network configuration would lead to a scenario where this wouldn't work.
When you switch a VM, when you schedule a switch of VM, there's overhead. And and to make the time dilation accurate, you want to make sure everyone doesn't run so long, right? Then that means the overhead gets bigger. And then if every VM is running a CPU-intensive, really CPU-intensive application, then after time dilation, you won't get 10 times as a single machine would get because there's no overhead.
So that's a great point. And one of the nice things about time dilation is that you can tweak it more till you get the right results, right? So for example, if you are seeing that the overhead is high enough that you're not able to cope with it with the current time dilation factor, you can increase the time dilation factor so that you have more real time to accomplish the same amount of work. And so for example, if you were running at TDF10 and you're seeing that you're not getting the same amount of CPU inside the virtual machine, you can increase the time dilation factor to TDF of 20, restrict the amount of CPU that the virtual machine gets such that after time dilation it will still get a maximum of whatever the CPU in the original system was, but now you have more time to actually finish those operations. So we can accommodate some of the overheads in that way.
Anyone else? Carlos, thank you, speaker again.
Thank you.